Alright, so this is going to be the first of two videos on this problem of diagonalizing a matrix. In the previous video we saw that similar matrices have the same eigenvalues. And so it's interesting to look for cases where your matrix is similar to a triangular or even better diagonal matrix, because for a triangular or diagonal matrix you just have to look at the numbers down the diagonal and those will tell you what the eigenvalues of your matrix are going to be. But we also saw in those last few examples that we looked at in the previous video that when you have a repeated eigenvalue, you might get more than one eigenvector coming with that eigenvalue, and you might not. And that kind of question of how many eigenvectors come along with a repeated eigenvalue is very closely related to this question of whether or not you can diagonalize a matrix. Okay, so what does it mean to diagonalize a matrix? Well, we say that we can diagonalize a matrix A if A is similar to a diagonal matrix. So if you can find an invertible matrix P, so that when you do P inverse times A times P, you get a diagonal matrix, right? And so we know that similar matrices have the same eigenvalues, so if A is similar to this diagonal matrix D, then we know that the diagonal entries of D have to be the eigenvalues of A. And one of the things that you can show, and it takes a bit of work, and essentially this the proof of this theorem down here, we'll see that to some extent the proof of this theorem falls out from just kind of looking at the procedure of how do you go about diagonalizing a matrix. It turns out that the way you diagonalize a matrix is you find the eigenvalues, then you find the eigenvectors, and if you have enough eigenvectors, to form a basis for all of Rn, then you can diagonalize. And this matrix P, okay, the columns, we'll see that the columns of P are going to be the eigenvectors, right? Now, remember that for a matrix to be invertible, the columns have to be linearly independent. So you have to be able to find enough linearly independent eigenvectors, right? It's an n by n matrix, so you need n linearly independent eigenvectors, and a basic theorem of linear algebra, one that we don't prove this in 1410, but in 3410 you would prove that anytime you have n linearly independent vectors in an n-dimensional space, you're guaranteed that they form a basis. So enough independent vectors automatically span. Okay, so if you have a diagonalizable matrix, then we can compute the trace and the determinant of our matrix, because we also saw in the previous video that similar matrices have the same trace and determinant, and since we know what the trace and determinant of our diagonal matrix is, right, if this is our matrix D, right, we know that the trace is given by just summing down the diagonal, right, so the sum of the eigenvalues must give the trace, and the determinant is the product of all the diagonal entries, so the product of the eigenvalues gives the determinant. If you can diagonalize your matrix, then we can compute trace and determinant, right? If you can't diagonalize, whether or not these remain true, actually it will be true in general that the determinant is the product of the eigenvalues, but you do have to allow for the possibility that some of those might be distinct, or sorry, might be complex. So there are some kind of issues to deal with there. But in general, this is sometimes a useful bit of information, that trace and determinant can be computed in terms of eigenvalues. Okay. Now, one of the important facts about eigenvectors corresponding to given eigenvalues is that if you take a collection of different eigenvalues, so if none of these eigenvalues from lambda 1 up to lambda n, if no two of them are the same, then you're guaranteed that this collection of eigenvectors corresponding to those eigenvalues will be linearly independent. Okay, the proof of this it's not going to fit on one slide. There's a fair amount of work to proving this result. Some of the details are given in the textbook if you want to see it. But a consequence of this fact is that if we have n distinct eigenvalues, so if all of the eigenvalues are different, so and this is the case of an n by n matrix, right? So the two n's here, they match up. Okay, n eigenvalues for an n by n matrix, and each eigenvalue is different, so there are no repetitions. If you have n distinct eigenvalues for an n by n matrix A, then you're guaranteed that you can diagonalize. Why? Well, because if you have n distinct eigenvalues, each one comes with an eigenvector. Those eigenvectors are guaranteed to be independent, and so you've got enough to form a basis. Right? So this is a standard result. If you don't have any repeated eigenvalues, you're guaranteed that you can diagonalize. Okay. So as a quick example, let's say we want to determine whether or not this matrix can be diagonalized. So if I wanted to decide, well, the chances are we're going to apply this previous result, but in order to apply it, the first thing I've got to do is I've got to find the eigenvalues. So let's see, what does the characteristic polynomial look like? Okay, so determinant of x times the identity minus a. Again, I like to do x times the identity minus a because I like the way the polynomial comes out. If you're worried about making sign errors, there's nothing wrong with doing a minus x times the identity. You can do that instead if you want. But I'm going to do it this way. Okay. So what do I get? I get x minus 2, 0, minus 2, 0, x minus 2, 1, minus 1, 1, x minus 4. All right, 3 by 3 determinant, so we've got to expand, right? With the x's in there, it's kind of hard to simplify using row operations. So let's just try to expand along. Let's go along the first column. So I've got x minus 2 times x minus 2, 1, 1, x minus 4, minus 1. That's this minus 1 right here. This guy. Okay. Minus 1 times, if I delete row 3, column 1, I'm left with 0, minus 2, x minus 2, and 1. Okay. So I've got x minus 2 times, so I've got x minus 2 times x minus 4, that's x squared minus 6x plus 8 minus 1 from the off diagonal. And here I've got, so I'm going to have minus 2, okay, so overall minus sign, right? Because I've got a minus 1 out front, a minus 1 there, and this is the off diagonal, so another minus 1. That's 3 minus signs, 2 times x minus 2. And you might be tempted to expand everything, collect terms, and then see if you can factor, but notice you've got a common factor, x minus 2 in both, okay? If you can do this sort of group factoring, you're much better off. So we pull out the common factor, x minus 2, leaves me with x squared minus 6x. Here I've got plus 7, but I'm subtracting 2, so that leaves me with 5, okay? So now I've just got to factor that quadratic, and that's something I can handle. I get x minus 1 times x minus 5, and so I get lambda equals 1, 2, and 5 are my eigenvalues. And notice that I've got 3 eigenvalues, and they're all distinct. And so that means, and we aren't doing the diagonalization yet, and I, you know, it takes a while to do a diagonalization problem, so fitting one into a video is sort of time prohibitive. But we can, at the very least, we can conclude that A can be diagonalized. Okay. If we wanted to go through the remainder of the diagonalization procedure, we would have to find eigenvectors for each one of these eigenvalues, form this matrix P whose columns are given by those eigenvectors, then find the inverse of P, then multiply everything together to see that we do indeed get a diagonal matrix with the eigenvalues down the diagonal. But that's a lot of work. That's a good, that's another 10 minutes of work that we're not going to try to squeeze into a video that's already long enough.